In this video, we're going to look at how to find the domain and range of certain functions. The focus for this video is going to be on rational expressions, but we'll have a few others just to introduce some shortcuts also for these functions. And again, when we talk about the domain and range, we're focusing on just real numbers. So whatever we give for the domain or the range, it has to be a domain consisting of real numbers. So let's look at the first one. Very basic, f of x is equal to 1 over x. Pretty much the simplest rational function you can have. For the domain, all we do is look at the denominator. We cannot have division by 0. So we have to restrict all numbers and make the denominator 0. In this case, it's 0. So the domain in this case is a set of all x such that x cannot be 0. So I can write it in set builder notation like that. Sometimes you can write it fast in interval notation. So this includes everything to the left, negative infinity to 0. From negative infinity to 0, but not including 0. And from 0 on, not including 0. So negative infinity to 0, union 0 to infinity. So if you have the rational expression in this format, again, you look at the denominator. Now if you want to find the range, just make this a y here, and then solve the equation for x. So let's multiply both sides by x. X cancels on the right side, and we get this. This one is solved for y, and we look at the restrictions on x. Now we're going to solve this one for x. I get x is equal to 1 over y. Now we look at the restrictions on y. Again, y is in the denominator, cannot divide by 0. So for this one here, it's a set of all y, not equal to 0. So this would be a range. Domain is set of all x except 0. The range, the set of all y except 0. Now for the second one, a little bit more involved, but you would do the same thing. Domain, no problem. It's solved for f or y. We look at the denominator. What number makes the denominator 0? Well, 5 minus 5 is 0. So x can be any number except 0. We just write it in set notation. So we can just write the set of all x, and that's the way you read this. This is a set notation here. Set of all x such that x does not equal to 0. So that's the domain. Now, to get the range, you could take this equation right here, this function right here, and solve it for x, and then look at the restrictions. But what I want to do is give you a shortcut here. So let's suppose you have the rational expression in this form. So this would be, it could be given as f of x or y. If it's given as f of x, just put a y there and solve it for x. So went through the steps here. Multiply both sides of this by cx plus d, and you get this right there. And then bring your ax term over, becomes a minus ax. Yd goes over, and then what we're going to do is solve it for x. So here I took out an x, got x parentheses yc minus a, on the right side minus yd plus b, and then divide by this. I get x is equal to minus yd plus b over yc minus a. What's the restriction? Set this equal to 0 and solve for y. So we get yc. Take the a over, divide by c. We get y is equal to a over c. So if you place the y by a over c, I get a 0 in the denominator. That's undefined. So that's why we have this range right here. So here's the shortcut then, if you have a rational function in this format. And I want to emphasize, it has to be in this form. In other words, the numerator has to be linear. You got x to the first there. Denominator has to be linear, x to the first. I can't have an x squared. This is not going to work in general. It's not going to work if this is an x squared. It has to be x to the first, x to the first. If that's the case, then you do the domain as usual, okay? What makes the x plus d equal to 0? Solve this, set this equal to 0, and restrict it. X will be minus d over c. So that's going to make it 0. So we restrict it. Now the shortcut to get the range is simply take, notice from the setup here. Just take the coefficient of the x on top over the coefficient of the x on the bottom, a over c, restrict it. Y cannot equal to a over c. Now, if it turns out that you have to have a linear factor for sure in the denominator. Now, if a is equal to 0 and you only have this, no x, so the a is 0. So y cannot equal to 0 over the c. The restriction is going to be 0 whenever the a is not there. Other than that, if there is a coefficient of x, then it's just a over c. Y cannot equal a over c. So let's look at how it works out over here then. So for the domain, let me do it this way. So here it is for the first one then, or I should say the second one. So this will be the domain then for number 2. We look at the denominator. What number makes the denominator 0? 5. So x cannot be 5. Domain then, restrict the 5. For the range, we use the shortcut. It's a over this c. So y cannot be 2. So domain for number 2, every number except 5. Range for number 2, every number except 2. Now for number 3, looking at the domain now, just look at the denominator. What number makes this 0? Take the 5 over, that's 7x. Divide both sides by 7. So for the domain, it's all numbers except 5/7. Now for the range, again, we look at the shortcut. So it's coefficient of the x on top over the coefficient of the x in the bottom is 3 over 7. So it's everything except y cannot be 3/7. And that's your domain and range for the third one. Now for number 4, for the domain, this will be your domain here. Look at the denominator. What number makes its denominator 0? That's the one we have to restrict. So you set this equal to 0, solve it for x. Bring the 5 over is minus 5 and then divided by 2. Restrict everything except, or I should say the domain is all real numbers except negative 5/2. So it's a set of all x for the domain, is a set of all x except negative 5/2. For the range, we look at the shortcut. X, 2 here. The coefficient of x is 1, so it's all real numbers at y except 1 over 2 or 1/2. Okay, so that's the shortcut you can use. And again, I emphasize that this procedure applies only when you have a linear factor in the numerator, a linear factor in the denominator. Now, if this didn't have an x here, that means the x is 0 here. So if this was just a minus 2, the x here would be 0. So the restriction on the y would be 0 over 2. So it would be any number except 0. So y could be any number not equal to 0. Now if there's some that do have like a square on the bottom here and stuff, those can be still done using regular techniques. Sometimes you'll have to look at the graph and so forth. For example, number 5. This method is not going to work for number 5 for the most part. In general, it's not going to work. But let's look at the domain first. So we got f of x is equal to 10 over x squared plus 2. 10 over x squared plus 2. What real numbers make the denominator 0? X squared plus 2. Well, again, x squared is never going to be negative. The smallest it can be is 0. And then you get a plus 2. So the domain, no restriction on x in. Denominator can never be 0. So it's all real numbers, or I can say negative infinity to plus infinity. So the domain again for this one. In negative notation, negative infinity to infinity. That's all real numbers. Now what about the range? See, this is one where the method I just went over, the shortcut method, doesn't work. Let's pick some values here. If I let x be 0 here, I get 10. That's a 0 here, and 2 is 2, so it'll be 10 over 2. So when x is equal to 0, the graph intersects the y-axis at the point 0, 5. And then what happens as x gets large? Say x is 10, 20, or negative 10 or negative 20. What's happening is the denominator gets larger and larger. So the y values get smaller and smaller. So actually that graph comes down like this. It never gets to 0. The denominator gets larger and larger, and the y value gets smaller and smaller. So it approaches the x-axis this way, and going the other way, it approaches the x-axis. So actually the x-axis is a horizontal asymptote. So for the range, the y value gets real close to 0, but the largest it gets is right there. So that's 0, 5. So for the range, we can simply say in interval notation, it starts at 0. Notice I have parentheses here because the graph never touches the x-axis. So this is open here, parentheses, and then it goes all the way up to 5. It does include the 5, so this one has brackets here. So that's your range from 0 to 5. Now the next one, f of x is equal to 30 square root of 36 minus x squared. Let's call this y. This again is one that we could look at the radicand here. And we know that we cannot take the square root of a negative because that would be imaginary. We're looking for just real numbers for the domain. So one way to get the domain is to solve this inequality. We know the radicand has to be greater than or equal to 0. So you can solve that. And let's do it this way. This factors into 6 minus x and 6 plus x. And then we can draw a number line over here. It's okay, this is going to be 0 at 6. And this is 0 at minus 6. So let's draw a little graph here. So notice if I pick numbers larger than 6, say 7. 6 plus 7 is positive, 6 minus 7 is negative. So in here, this will be negative. If I pick numbers less than negative 7, this will be negative here. This will be plus negative 7, minus here, this will be plus. This will be plus, but because this is negative, this over here will be negative. Now if I pick a 0, 6 minus 0, 6 plus 0 is positive. So this is positive in here. So that tells me that this 36 minus x squared is going to be greater than or equal to 0 for all numbers between negative 6 and 6, including negative 6 and 6. So one way I can give this domain, because the negative 6 and the 6 is included, I use brackets. And I say domain is from negative 6 to 6, including negative 6 and 6. Now for the range, let's replace the f by y, and let's square both sides. I get y squared is equal to 36 minus x squared. Let's take the minus over to the other side. Minus x squared to the other side to be x squared plus y squared. Now this you should recognize this as a circle. R squared is equal to 36, so that means the radius is equal to 6. So this is a circle of radius 6. So let's say this is minus 6 over here, and a plus 6 over here, and a 6 up here. 0, 6 is that point, and the graph looks like that. Doesn't look like a half circle, but let's suppose it does. So that's what the graph looks like. And it's only the top half because this is a positive here. Whenever you have the square root of something and it doesn't have plus or minus, that means it wants the answer to be positive. So we take the upper half. Well, see, from this one, if you have the graph, you can find the domain and the range. So the domain, of course, we found it by solving this. But look at from the graph, you can also find the domain. It's between negative 6 and 6. There's no values over here or over here. Everything for the domain is between negative 6 and 6. So that's your domain. Now what's the range? Those are the y values. So what's the smallest y value we can have? This point right here is negative 6, 0. This point over here is 6, 0. And then I have a point up here because the radius is 6 of 0, 6. So the range goes from 0. Smallest point, smallest value for y will be 0, and the largest value will be 6. That's your range and domain. Now, number 7 is a polynomial function. That's why I used P. I could have used F again, but a polynomial function. So you have parabolas that open up, parabolas that open down. You have the cubic third degree polynomial. The most basic one is y to the third. And that has a graph that goes like this, passes through the origin, then it goes up like that. And here are the shortcuts for polynomials. The domain of a polynomial is always going to be all real numbers. There's no restriction. You can't have any division by 0. You don't have a square root, so you don't have to worry about imaginary numbers. Any number can be replaced for x. There are no restrictions on the values you can substitute in for x. So the domain is always going to be all real numbers, negative infinity to infinity. Now, if you have an odd degree polynomial, and this one we do, it's 5. It always has a graph kind of like this. It goes up at one end and down at the other end. Now, if you have like a 5th degree or a 7th degree, you could have something that goes like this. It might have several loops, but it's going to go up at one end and down at the other end. So as long as it's odd degree, 3, 5, 7, 9, the range will also be all real numbers. That's the shortcut for polynomials. You have an odd degree. Well, first of all, for any polynomial, the domain is all real numbers, minus infinity to infinity. But if it's odd degree, the range is also all real numbers. Okay, so those are your tips for that one. Now, if you have an even degree, like a parabola, see this one goes up, this one goes down. You have some others that might go like this. They either both sides go up or down. Domain is still going to be all real numbers, but the range is not going to be all real numbers. It's going to depend on, in this case, it'll depend how low this point is here. That's going to determine the range. And that's going to be beyond algebra. You have to use some more advanced techniques that you get in calculus. But those are just some of the tips for finding the domain and the range. Thanks for watching. We'll see you next time.